In my previous video, I showed you the proofs of a bunch of formulas about triangles. They all come from this image, and they were the formula for the area of a triangle, the sine rule, and the cosine rule. So after I posted that video, a few people asked in the comments if the same proofs could also be done for the cases where the theta was an obtuse angle. So I thought that I would complement that by showing that yes, the same things work exactly the same when theta is an obtuse angle. It's going to be a pretty little thing to look at. But I will go over those formulas a lot faster this time because I already did it once. And in the other video, I also made a bunch of other comments, which I don't have to repeat. And then I am going to continue in this video by proving yet another formula that I didn't think to do in that video, which will be the double angle formula and the compound angle formula. Okay, so we'll go over that as well in this video. So first of all, quickly, just to summarize all of the demonstrations that I did in the other video, it all has to do with this height that we can trace in the middle of the triangle here. And of course, by height, I mean something that is perpendicular to one of the sides of the triangle. So because it is perpendicular, you can now see two right triangles, one in the left and one in the right. And you can measure the height as a projection of this side with this angle going this way, or the same thing on the other side, this side projecting with that angle, and those have to be the same thing, which is the demonstration of the sine rule right here if you just divide by both sides. And it's also the demonstration of the area formula for the triangle. If you go base times height divided by 2 with this height, then you get the formula b times a times sine of theta divided by 2. And the cosine rule also comes from the same picture by looking at the projection of a with cosine down here. So now you have a cosine theta over here. The whole side was b, so this side is b minus a cosine theta, which you can then do a Pythagoras on this right triangle on the right side here. So now I want to talk about how these things would look if we were talking about an obtuse triangle instead. And it is going to be the same thing, except that in order to trace the height as something that is perpendicular to one of the sides of the triangle, I'm going to have to make this side go longer a little bit here to the left. So the area of a triangle is still base times height divided by 2, even in situations like this where the height actually falls outside of the triangle. And this is also going to lead us to a times b times sine of theta over 2, because this height is still a times sine of theta as a projection over here. But in order to see it in this triangle, you actually need to be aware of the unit circle and the fact that the sine, which is the vertical coordinate of these points here, so there is a symmetry here, right? Because this theta is the same as that theta over there, which means that the sine of the angle pi minus theta is equal to the sine of the angle theta, and that is valid for every angle. But in our triangle, the right triangle that we are using to project here the side a to the height h, we're actually using the angle pi minus theta out here, which belongs to the right triangle. We're not using that theta over there, which we wanted, but it's okay because pi minus theta and theta, they have the same sign. So you can write the height like this and use it in the triangle area formula, base times height divided by 2. So you will get the same formula as you were getting when we were looking at it this way. And as for the sine rule, it is the same thing. We are still measuring the same height, the same segment in two different ways as two different right triangles. One of them is the same small one that we were just looking at just now, and the other one is this big one right here, all the way over there. So for that one, the projection would be with the angle alpha. C times sine of alpha is the height. And the height needs to be the same length as we measured with the other angle, pi minus theta, which is the same as the sine of theta. So the sine rule still works here. Again, because we will divide both sides of the equation first by the sine of alpha, canceling those ones over there. And then we will divide both sides of the equation again, this time by the sine of theta. Canceling these ones over here, and once again proving the sine rule the same exact way as I did in the other video with that picture, but this time I did it with this picture, which has an obtuse angle, just to show you that it doesn't matter. It's any angle, the rules will be proven in the same way and can be used in the exact same way. Now, in order to prove the cosine rule in this picture, it's going to feel a little bit different than the other one did, but it's not different. It's just going to feel a little bit different because the green segment here is projected again with pi minus theta, so that makes it 8 times the cosine of pi minus theta. But the cosine of pi minus theta is not equal to the cosine of theta. The symmetry of the picture is still here, but in this case, one is on the right side of the coordinate plane and the other is on the left side, making it a negative number. So the correct observation this time is that the cosine of phi minus theta is equal to negative the cosine of theta. And we're going to use that over here. Because now, when you look at this big segment on the horizontal here, it is b plus a cosine of pi minus theta, which is different than what was happening here with the purple segment because it was smaller than b, so it was b minus something. That one is plus. But I don't want to make a formula with cosine of pi minus theta, right? I want to make a formula with the cosine of theta. So I'm going to use this to substitute here the cosine of pi minus theta with minus cosine of theta. So that's going to make this into a minus anyway. So now when you do Pythagoras in the big purple triangle here, it's going to look exactly the same as it did in the demonstration for the other picture that I did in the other video. Then you expand the terms, cancel out the things that need to be canceled out, and you will get the same formula again. So of course the formula needs to be the same formula, right? It wouldn't be a lot of fun if you had one formula to use in acute triangles and a different formula to use for obtuse triangles. Usually we don't have to prove the same formula twice, but in this case I thought that it was fair to ask for that because the pictures do look quite different. So it was nice to check that it comes to the same result in the end. But the reason why all of that works is because the unit circle is the way that it is, right? It worked because it's centered in the origin, because it has some positive cosines and some negative cosines. So I don't know, some people would like to say maybe that, oh, so this is why somebody invented the unit circle to look the way that it does. It was so that this would work out perfectly. I don't particularly care why people invented something, what they were thinking. The point and the beauty of math is that all of these things are coherent with each other, right? They all make sense and work in the same way. It doesn't really matter who came first or why. Okay, so let's move on to formulas that were not mentioned in the previous video. I said that I was going to prove the double angle formula and the compound angle formula. But I'm actually going to prove just the compound angle because you will see in a minute that the double angle is just a special case of that. So I have an angle A here in my triangle right now, and in a minute I'm going to have a second angle, which I will call B. And I know that SL students only have to know the double angle formula. They don't have to know the compound angle formula. But if you are an SL student watching this, when I put the B in there, just pretend that B is A. Then you will have two of the same angle, and it will be the double angle formula that you do need to know. Okay, so here's a right triangle, and the proof is going to start from this triangle, but I need to put a second right triangle here, and I wanted to draw that together with you because it's a little tricky how we are going to draw it. It's not going to have one leg in the horizontal and one leg in the vertical, which is the usual way that you draw right triangles, and you find it easier because you're used to doing it. But for this next triangle, I want the hypotenuse of the first one to be one of the legs. So I want the second leg to be perpendicular to this hypotenuse. So I'm going to draw a second right triangle there, but it's going to be kind of like this. Okay, so if you're following this, making your own diagram on paper, it is important for you to draw a right angle there. And that's going to be your second right triangle, so you can go ahead and close this thing with what's going to be the hypotenuse of the second triangle. And then there's the angle B that I was talking about. Because the compound angle formulas are interested in the sine of a plus b and the cosine of a plus b. The easiest way to look at sines and cosines is inside of right triangles, which is why I'm drawing right triangles. And the fact that I want a plus b is the reason why I'm drawing them this way, because now the red one is a plus b, so I can try to look at its sine and its cosine, and then I'll get what I want. But I'm going to have to be a little bit smart about how I do it, because the angle a plus b is not inside of a right triangle right now. It is inside of maybe a quadrilateral made up of two triangles. Okay, so let's slow down a little bit moving forward. I want to call the hypotenuse of the second triangle 1. That is just going to simplify my calculations a little bit. A lot of people get nervous when I just choose a number like this, but it's just one number in a picture, and I'm going to be working with ratios because sines and cosines are ratios. It's the opposite leg divided by the hypotenuse. So if I chose a different number, it wouldn't matter. I do have this freedom to choose something here, because it doesn't matter if this picture is small or big. The conclusions that we're going to get to are about the angles. So yes, I can choose a number. Of course, I can't choose anything else right now, because once I put the 1 there and the angles are already named, A and B, now everything is already determined in terms of A and B. I can't choose anything else. For example, that segment there is sine of B, because sine of B over 1 is the sine of B, the opposite leg divided by the hypotenuse. But of course, if you've already watched the previous video, you know that I don't even like thinking of it this way. I am just looking at the hypotenuse, which is 1, being projected over there. So the projection away from the angle is sine. And this other segment here is the projection over the angle B. So that's cosine of B. So the green segment there is cosine of B. But the green segment is the hypotenuse of the first triangle, right? And the first triangle has an angle A. So if I take the green and I project that onto the other sides, then I will have the measures of these legs. So this one is projecting the hypotenuse over the angle A. So it's going to gain cosine of A. It's the cosine of B that was already the length of its hypotenuse times the cosine of A that it got from being projected. And this vertical leg here is going to be the same hypotenuse, but with the sine of A, because it's projected away from the angle. And hopefully at this point, you're already starting to see where the sort of terms that appear in these formulas are coming from, right? Because you know what the formulas look like. They have sines multiplied by cosines, and that's where that comes from. But I haven't done the smart thing yet. The smart thing is going to be to measure that vertical red segment that I just put there, because that's what's putting my angle of A plus B into its own right triangle, which is this red dotted triangle over here. And I already know the hypotenuse of the red triangle, right? So if I'm able to measure the red segment, I am already going to have the sine of A plus B. And then I'm going to do something similar in the bottom to get the cosine. But let's try to measure the red segment. That's going to require something even smarter. I have put an orange horizontal segment here. I'm not sure if you can see the difference between orange and red in the camera, but trust me, this one's orange. So I am going to measure the big vertical segment as this part plus this part, okay? And the bottom part is just this, because this thing here is a rectangle. And in order to measure the top part, I am going to be looking at this blue triangle here, but it's looking quite small. So let me copy it down here a little bit bigger. Okay, now look at the very pretty things that are going to happen. The orange segment is horizontal, and so is this black one down here, the very first one that I put in the picture. And the green segment here is kind of diagonal to it. So it's like a line crossing two parallel lines, the black one and the orange one. And you know that a lot of interesting things happen when a line crosses two parallel lines. One of them is this angle here, which is A, is going to be the same as this angle here, which is now also A. But in the big picture that we can see things better, it's here. Here's the angle A. Now this was a right angle, so that means that the part of this angle here that is in the triangle that I'm interested in, that's pi over 2 minus A to make it into a right angle. But now if you look at my triangle, it has a right angle and an angle of pi over 2 minus A, which means that the third angle here in the top, that's A as well, just using the fact here that the sum of all of the three angles in the triangle have to add up to 180 degrees or pi radians as we are looking at it. In fact, I don't really know why I'm doing this in radians. I might as well have written 90 degrees minus A here. It would have been the same thing. Anyway, the important conclusion is that this is A. This is A inside of another right triangle whose hypotenuse I know. So I can use projection with this angle to figure out the lengths of the legs. The vertical one has the value of the hypotenuse, which used to be sine of B, and getting a cosine of A multiplied by it because it is projected over the angle. And the horizontal one here is going to get the sine of A multiplied by the hypotenuse. And that was the last piece that we needed. Because remember, we wanted to measure this vertical red segment here in order to call it the sine of this angle A plus B here by looking at the big red triangle whose hypotenuse is 1. That's a very long path, but it is what we're doing. So we had already measured the bottom part of the red segment as being this. Now we just have to add it to the top part, which is this, and divide it by the hypotenuse, which is 1, which is giving us our desired result of the compound angle formula for the sine of A plus B. Now for the cosine, we need this bottom segment here, and it's almost ready because cosine A times cosine B is the big one, but we don't really want the big one. We want just this red part here, which belongs to the right triangle we're looking at. So we need to subtract this part here. But this part is just this part. So you subtract that from the length of the big segment and you get the compound angle formula for the cosine like we wanted. So by the way, this is one of those things that I don't really understand about the choices of content to be in SL or HL. Because it's not like you really have to demonstrate the formulas, especially in an SL class. But the demonstration of the double angle formula is not easier than this. It's the exact same thing as this, only instead of A and B, you just have A. But you still have to do the same pictures and you still have to draw all the same auxiliary segments and look at all of the smart little things like we did here. So this is a really difficult demonstration. I really don't think it is necessary, especially for a standard level. But my point is just that the other one is not easier. So if you're going to have one of them, why not both of them? And as for the application of the formulas, first of all, I also don't see one as being more difficult than the other because it's just plugging numbers into A and B. But on the other hand, even for HL, I think it's quite rare to see a question that requires the compound angle formula. The double angle formula appears a lot more often. And by the way, since I'm mentioning this over and over, I might as well write it down, right? This is the double angle formula coming from the compound angle formula. You just put in A plus A as 2A instead of A plus B, and then you plug them in and it reduces to this. Same thing happens for the cosine of 2A. As for the compound angle formulas though, what are they useful for? So when I first saw this, the first thing that came into my mind was that they were going to help me to actually know the sines and cosines of more angles, because one thing that is very frustrating is to only know concrete numbers for 30 degrees, 45 degrees, 60 degrees, and all of the variations of those in the other quadrants, right? And there is one angle that you can get the sine and the cosine for quite easily by doing this, which is 75 degrees, which you never knew the sine and cosine of before, but it is 30 plus 45. So you can use the compound angle quite easily to figure out the sine and cosine of 75. I'll let you do the cosine as an exercise. But then that's pretty much it. Because if you try to add up pairs of other angles that you know, you start to get to the same numbers. Like 30 plus 30 is 60. Well, I already know that one. 30 plus 60 is 90. Oh, I already know sine and cosine of 90. And then is there maybe something that I can do with 75, the new one? Well, 75 plus 75, again, I don't know, 150. I kind of already know 150, don't I? Because it's 180 minus 30, so I know all of the symmetry. You can get to 15. You can get to 15 with 45 and negative 30. But 15 also doesn't really give you all that much more, because if you add 30 plus 15 is 45, 45 plus 15 is 60. It's all of the same numbers that you already knew. It's really tempting to start trying to do things like this. For example, you got 15, right? So you wonder about 10. Can I get to the sine of 10 degrees? Well, 10 plus 20. 20 is 2 times 10, right? Maybe I can do one more step. And I do know the sine of 10 plus 20 because the sine of 30 is a half. So maybe I can manipulate those things in some way. Go ahead. I encourage you to give it a try, but it doesn't result in easy equations to solve. What this kind of thing tends to result in is equations that you would have to use a calculator for. But then again, if we're trying to do this with a calculator, then there is no point of doing it at all, because with a calculator, we already have all the sines and cosines of numbers that we want. Which brings me back to a much older point that I made in a much older video about solving trigonometric equations, is that, first of all, trigonometric equations wouldn't be an interesting question in a paper 2, right, with a calculator, because you would just type the equation and find the intersection of the left-hand side with the right-hand side. That's not interesting. So it has to be a paper 1 question. But if a trigonometric equation is going to be a paper 1 question, then you already kind of know what the answer is, because the answer is either 30 degrees or 45 degrees or 60 degrees. Maybe 75 if they're feeling very adventurous with a question. I'm going to give you something really difficult to do, but that's it. So when I start solving a question and I already know what the possible answers are, that is very much not satisfactory for me. So anyway, I don't think I remember having even seen the compound angle formula appearing in a trigonometric equation kind of exercise, but the double angle formula does appear quite often. It's like they'll ask you to solve a trigonometric equation, and then one of the things that you have involves an x, and the other thing involves a 2x. So it's one equation talking about two different angles. That is very complicated unless you reduce them to be talking about the same angle. The standard way to do that is by using the double angle formula here. That's looking a little bit better. It is still one equation using both sine and cosine. So usually what I want to do in that kind of situation is to just choose one of them and convert the other one. In this case, I am definitely going to change the cosine into sine by using the Pythagorean identity and not the other way around. Because if I was going to convert sine into cosine, then there is a sign here that is not currently squared. So if I wanted to use the Pythagorean identity, I would have to get a square root, and nobody likes that. So of course, when you reorganize that, you get a quadratic equation in the variable sine of x. Please solve it in your favorite way. Don't give me a hard time for not factoring. I like the quadratic formula. And you get two options for the value of sine. Sometimes one of them will be an impossible value because sine of x needs to be between -1 and 1. But this time it didn't happen. This time they are both valid values of sine. And the only other thing you still need to do in this question is to figure out what are all of the angles within the given domain in the question that have one of those values of sine, because this is a very common mistake, is for people to say the first angle that comes into their mind whose sine is a half, which of course the first one that will come into your mind is 30 degrees, but then forget to look for others within the given domain of the question. So this question says from negative pi to pi, so it is one full circle, but it's not one full circle going this way. It's half of a circle this way and half of a circle the other way, which means that the value that we are looking for here is negative pi over 2. The first one that comes into our minds that I have already mentioned is that one over there, which is pi over 6. And it does need to be given in radians, okay, because the question asked you in radians. It gave you the domain in radians, so please don't answer in degrees. That's a silly mark to lose. But also silly is to forget the other angle over here, which is still inside of the domain because it's less than pi. That is 5 pi over 6, just from the symmetry with the other one. So that's it. This question had 3 solutions. I'm not going to do more trigonometric equations here because I already have other videos doing that, and like I said, they are very frustrating in their lack of variety of answers. Of course, if you're about to take an exam, then that's a plus, right? You know that the questions are pretty much always going to be the same question, so you can do it, you can get your marks.